Welcome to lecture 24 of our system protection course. In the last lecture, that is lecture 23, we have discussed about the busbar protection schemes, and mainly we focused on the differential protection scheme of busbar protection, and in that we have seen that how the external fault in fact affects the differential scheme, and also we discussed that how the high impedance busbar protection scheme being developed, and we derived the equation for stabilizing resistance, and then we found also minimum internal fault that can be detected by the high impedance differential protection scheme. So in this lecture we will little bit more cover the busbar protection, where we will see that when there is some open circuit happens at the secondary side of the city, in fact it is difficult for the overcurrent relay which is being installed in the spill path to detect this kind of fault. So therefore a different kind of protection scheme is being developed for this, and we will discuss about that is called the supervisory protection scheme. And also we will talk about the generator protection. So let us start with, let us first talk about the supervisory relay. So what is the importance of it? So here we are considering a busbar protection scheme where we have two incoming feeders, as we can see here, that is IA and IB, and one outgoing feeder, that is the current is flowing in the outgoing feeder is IC. And suppose, let us say that the secondary wire that is also connected to the pilot wire, where there is a breakage happen and the wire become open circuit. So it's the open circuit condition, right? So under this open circuit condition, what happens that your whole, if here the open circuit happens, then the IC flowing in the secondary side, that will in fact flow through this resistance, flow through this relay. Okay, so therefore this relay will trip. And hence, in order to avoid this kind of scenario, just to detect or to raise an alarm over when there is open circuit, so there is an over voltage relay is installed. Okay, so that is called the supervisory relay, and this over voltage relay in fact detects the voltage across this high impedance connected across the relay, right? So that in fact when the current flows through this, and the voltage across this will be detected by this over voltage relay, and this gives the alarm signal, right? So that is called the supervisory relay. So the voltage, what will be the pickup voltage here in this case? The pickup voltage will be your I small c, that is reflection of this, which is flowing through R stabilizing plus R over current relay. This is the resistance of the over current relay, and this is the resistance of the stabilizing path. Okay, so now this will be your pickup voltage, right? Okay, so now you can see this is a scheme which is being implemented for a three-phase circuit, because in fact the transmission lines are all three-phase, and we have in the previous diagrams already we have always saw or will always analyzed that are all single line diagram, right? Single line diagram, based on the single line diagram, but we have not shown how this differential relay is being implemented in a 3-phase circuit. So if we'll consider a bus bar where your incoming feeders are 2 number of incoming feeders and 3 number of outgoing feeders. This is in fact shown for a for phase A only, here A phase, right. So for phase A, we can, the arrangement will be same structure as already we have discussed this with, this is the high impedance 3-phase bus bar differential scheme. Similarly for for phase B also we will have arrangement similar to phase A, and similarly for phase C also we will have the arrangement exactly similar to phase A and phase B, right. Okay. So this is the arrangement for a 3-phase system, or high impedance 3-phase bus bar differential protection scheme we call it. Okay. Now let us see an example that can illustrate the design of a high impedance differential scheme for a transmission system. So here a 132 kV bus bar is considered, which is being protected and which is consists of 2 incoming lines and 4 outgoing lines. Okay. So if this is your bus bar, okay, this is your bus bar, then it is in fact consisting of 2 incoming lines and 4 outgoing lines. Okay. So this is your bus bar structure where 2 incoming lines are connected and 4 outgoing lines are connected. The system is solidly earthed and the switchgear capacity is 3500 MVA at 132 kV. So the parameters are maximum full load current in one line, that is 500 ampere, right. This is the maximum full load current, and RS is your CT secondary resistance, already we have seen, and the value is given 0.7 ohm, and R lead wire, the lead wire pilot wire resistance is 2 ohm, and relay load, which is 1 ampere relay, that is 1 ohm, and CT magnetizing current up to 120 volt is 0.28 milliampere per volt. So it is linear, and CT saturation voltage, the knee voltage is considered at 120 volt. That means up to 120 volt it's not saturated, that is the knee voltage. So up to that point it is linear, so the voltage will be in terms of 0.28 milliampere per volt. So the question is, if the overcurrent relay in the spill path is set at 1 ampere and the voltage setting V set is 100 volt, then find the maximum through fault current up to which the scheme will remain stable. Okay. And question B is whether the answer in the part A is commensurate with the switchgear capacity. Our switchgear capacity is 3500 MVA, right. So will it in fact commensurate with whatever through fault current we are finding, for which the system will remain stable? We will check that. Question C is the minimum internal fault current which will be detected by the scheme. So what will be the minimum internal fault current? Okay, that will be detected by the scheme. Then question D is the setting for detecting minimum internal fault current of 500 ampere. When the minimum internal fault is 500 ampere, then what will be the setting? Question E is the value of the stabilizing resistance for D, for above question D. Find the stability ratio. And question 2 is, it is required that a break in the pilot wire from a CT carrying a current of 25 ampere and more should be detected by the supervisor relay. Calculate the setting of the supervisor relay. So we need to find the VPU, right, in this case. So what will be the setting voltage for pickup? Let us find the answer to question 1a. So let us choose 1 ampere CT. Therefore, because it is given 1 ampere CT, so therefore as explained in the text, as explained already, as we discussed, that CT ratio for all CTs, that will be equal to maximum of all feeder current, that is 500 ampere, is to 1. Okay. So how we will find the IF external maximum? We need the CT ratio N and V set and ZS. So V set is given, that is 100 ampere, and CT ratio we can find from the here, that is 500, and ZS is 2 plus 0.7. 2 is your resistance of the lead wire and 0.7 is the secondary resistance. Okay, so therefore it is 2.7. Now your IF external maximum, that is maximum external fault current that can be that can give the stable operation of the protection scheme, is 18,518.51 ampere. Okay, so this is now if we will see second question, question 1b, that is 1b is from the given data the maximum through fault current that can be handled by the switch gear. Switch gear rating is given 3500 MVA into 10 to the power 6 divided by the voltage, rated voltage, that is the current. This much of current will be handled by the switch gear, that is 15,300 ampere, right. So now the scheme remains stable up to the through fault current of this. Okay, already we have decided that the scheme will remain stable for 518.51 ampere, but the switch gear is designed to handle only 15,300 ampere. So therefore we need to substitute 15 instead of 18,518, we need to substitute 15,300 instead of in place of IF external max, right. So that is the maximum external fault current is 15,300 into 2.7. 2.7 is the resistance, right, across the secondary side, and 500 is the turns ratio. Now your V set will be 82.62 volt. So your voltage setting is changing from 100 to 82.62 volt. Okay. So now question number C is, if we will see question number C, that is now we need to find the minimum internal fault current for V set 100 volt and I pickup 1 ampere. So we know this formula, that IF internal minimum, which will be detected by the scheme, by the high impedance busbar differential scheme, will be N times I pickup plus small n into I naught. I naught is your magnetizing current, I pickup, and N is your CT ratio. So here CT ratio is 500 and I pickup is given 1 ampere, and N already we know 6 because N is the number of feeders connected to the bus, and IO is given as 0.28 milliampere per volt. So therefore for a voltage of 82.62 volt, so we need to take this volt instead of 100 because this will give us the minimum internal fault current, which will be, if this will give us the internal fault current which is also applicable to V set equal to 100 volt. So therefore IO will find by considering 82.62 volt, which we found when we are designing, when we are finding for V set for the rated MVA capacity of the switch gear, right. So for that we found IO is equal to 0.28 into 82.62, that is 0.02313 ampere. So it is very small, and thus IF internal minimum will be, in the primary side will be 500 into 1 plus 6 into 0.0231, that will give me 569.39 ampere, which is the minimum internal fault current that will be in fact detected by the scheme. The next is your for minimum internal fault current of 500 ampere, what will be the pickup value? Okay, so your pickup current will be, obviously the formula we know, that is IF internal minimum primary by N minus NIO. So n is, small n is 6 because 6 number of feeders are there. So it will be 500 by 500, okay, and then your pickup current will change from 0.5 to 0.861 ampere. Now question number E was to find out the stabilizing resistance, right? So from this equation we can find the stabilizing resistance. We know that R stabilizing plus ROC relay will be equal to V set by I per unit, I pickup, right? So then by substituting this, we will find the total resistance across the secondary side, across the spill path will be 95.93, and if we will subtract this ROC relay, that is 1 ampere, then your R stabilizing is 94.93 ohm, right? So this is your next is your so E is gone. Then next is your 2. Question number 2 is setting of the supervisor relay. Setting of the supervisor relay we can find by neglecting the magnetizing currents of the CTs, right? Just by neglecting, we can find B supervisory will be I load lost, which is lost, right? CTC is lost in fact. So one of the CT is lost, that is 25 ampere is given, right? So 25 by the CT ratio N into R stabilizing into ROC relay, that will give us 4.79 volt, okay. So this will in fact give us the setting of the supervisor relay. So this is all about your bus protection scheme. Now we will talk about the generator protection scheme. In fact, generator plays very important role. So a generator could be part of a water turbine based hydropower station, it could be a part of gas turbine based power station, or it can be steam turbine based thermal power station or nuclear power station, right? So therefore generator in fact connected, this is a turbo alternator which is being connected from all sides, right? If we will see from prime mover side, from the turbine side, the generator shaft is connected to the turbine, which we call the prime mover, right? And again the generator is connected with an electrical system, we call it DC excitation system, and in the another electrical side, that is the stator side, this is the rotor side, and in the stator side it is connected to the power grid. It is in fact supplying electricity to the power grid. Okay, so in case of a fault on a turbo alternator, it is not enough to open the main circuit breaker connecting it to the power grid. Just it will be not sufficient, because when a turbo alternator driven by a steam turbine is tripped, the following must be done in order to protect the whole system, because the generator is connected with many systems, many supplementary controllers, right? So now if you see, the steam supply of the turbine need to be stopped or bypassed. If it will not done, then it will create hazardous impact on generator. Then firing to the boiler should be stopped, coal mills are stopped, coal supply to the coal mills need to be stopped, field circuit of the alternator need to be interrupted, and the field coils, because it is an inductive coil, so it needs to be connected across a resistor to dissipate the stored energy. Alternator is kept running at a low speed with the help of bearing gear till it cools down uniformly, so as to avoid uneven expansion. So the alternator need to be kept running at slow speed. It should not be stopped immediately, right? So unless it is cooled down properly, right? Unless if it is not cooled down and we stopped, then there will be uneven expansion, because we know the air gap is very small, so it will damage the whole generator. Putting back the alternator online is rather a slow process, because all the parameters like temperatures, pressures have to be progressively built up to avoid thermal shock resulting in uneven expansions, which might cause unacceptable vibrations. So this is very important, because a huge mass is rotating with a very small air gap. So the attention must be there, the care should be taken if some uneven expansion should not take place. That will create a lot of problem, unacceptable vibrations. Therefore, unscheduled outage of a thermal power station is avoided as far as possible. So we have to keep in mind that a modern large turbo alternator is a huge mass rotating at a very high speed, around 3000 rpm. Generally, a two-pole machine runs at 3000 rpm in case of 50 Hz system in a very small air gap. Thus, apart from the large electrical energies involved, there is tremendous amount of mechanical energy in the form of moment of inertia of the rotating mass and the resultant forces on the shaft, the rotor body and the stator structure. Okay. So the entire system has therefore to be run in a narrow range of various parameters like temperatures, pressures and flows, right? Flow of the steam, voltages, currents, power factor, etc. So the operation outside the specified parameter range may cause a substantial decrease in the life of the equipment. So there are certain limits, a range of operating parameters, and it has to be maintained. If not, then the age of the equipment will reduce. Since the power station equipment represents a very high investment of money, it's crores of rupees, so the operation of the power plant is very closely monitored and controlled. It is very, very essential that there must not be any damage to any of the equipment, or it should be safely operated. So it may cause catastrophic disaster sometime if it is not very carefully monitored. Okay. Now if we'll see the generator, turbo alternator, how it is connected to different systems, right? We can see here, this is your alternator in fact, right? This is alternator where the rotor is on the shaft and these are the stator windings, right? And this is your exciter, where the exciter may be consisting of a DC machine, or maybe it is an AC exciter consisting of the rectifier circuit, right? So this is your electrical system. Now coming to the mechanical system, the shaft is connected to the turbine. We can see here the long shaft. So therefore the torsional vibration oscillation plays very important role in this on shaft. And here the turbine, we have two-stage turbine, it is shown here, high pressure turbine and intermediate or low pressure turbine, also intermediate pressure turbine, right? So we can see this is steam cycle. If we'll see, the steam is being provided by the boiler. We can see this is the boiler. So in the boiler the steam is being produced when the coal is burnt, and the coal is being fed by the coal mill, and when it is burnt inside the chamber, inside the boiler mixed with the oil, then it produces the steam, and steam goes to first it goes to the high pressure turbine, then from high pressure turbine it goes to the superheater, then from the superheater again it goes to the intermediate pressure turbine, then from intermediate pressure turbine to the low pressure turbine, right? Then from the low pressure turbine it goes to the condenser, and in fact this condenser is connected through a water cycle that is connected to a cooling tower, which in fact gives the cooling effect here in the condenser, right. And that in the condenser the steam is converted to water, and then again through the feed form it is fed to the boiler. This is the cycle. Sometimes it is called the Rankine cycle. It is a mechanical part, we should not discuss more about this. And we have, for exhaust, we have the electrostatic precipitator, right, and the induced draft fan which forces the exhaust gas through the chimney outside world. This is how it operates, and there are many components involved in fact, right. And the stator is connected to the grid here, we can see, right. It is the power transformer which is connected to the transmission line. So now if we will see the electrical circuit of the generator, because we should more focus on the electrical circuit, electrical protection system. We are not worried much about the mechanical part. So it is to be noted that the generator is never solidly grounded. If it were solidly grounded, the single line to ground fault current would be dangerously high. So therefore the grounding, the neutral grounding of the generator should not be solidly grounded. It is in fact done through, so apart from the high value of fault current, the resulting asymmetry in the rotating magnetic field inside the generator would cause unacceptably large vibrations and result in mechanical damage to the rotor. So these are the causes if we do the solid grounding, okay. Hence, in order to limit the short circuit current, the neutral of the generator is grounded through a resistance. So in order to get a practicable value of the grounding resistor, it is connected through a step down transformer, okay. So known as the grounding transformer. We will see the structure now. You can see here the structure of the grounding transformer here. This is your generator alternator. The neutral is grounded through a grounding transformer, which is a step down transformer, right. And at the secondary side of the transformer there is a grounding resistance, okay. So whatever current it draws, because of this the current in the neutral is limited, okay. So it limits the current in the neutral. Now the power plant has a sizable auxiliary electrical loads. We know that power plant has a lot of other electrical loads of its own, and of the order of 10% of the power rating of the generator. Whatever generators are installed in a plant, power plant, 10% of the generator's production or whatever the generator produces power, it is being consumed in as the auxiliary supply to the power plant, which is supplied through the unit auxiliary transformer. We call it UAT. It is to be noted that these auxiliaries require power even before the generator can be started, run up to the speed and synchronized with the grid. Till the synchronization of the generator to the grid, the auxiliaries require power. So therefore this power sometime is supplied from the grid, and it happens when we have some switching facility to energize this UAT directly from the grid, because unless the generator starts up to its rated value, it cannot provide to its auxiliaries. So till that point we in fact take this power from the grid, okay. So therefore there must be some switching arrangement in order to get this. So now if we'll see the arrangement, here the generator, here the auxiliary unit transformer, right, unit auxiliary transformer which provides to the auxiliary requirement of the generator, right. And this is your power transformer which is connected to the extra high voltage circuit through the main circuit breaker. So the rotor of the generator houses the field winding. Already you have studied in your machines course also, right. So the rotor of the alternator, it in fact includes, or it houses the field winding. a separate DC generator which is mounted on the turbo generator alternator shaft feeds the field. So sometimes a DC generator feeds, or we take the AC from the terminal of the generator and rectify it, and the rectifier in fact put on the rotor of the generator, and it feeds the field, right. So as you can see here that this is a generating system where the excitation system is here. So there must be some excitation control in order to control the field current, and it is put on the rotor, okay, and it is coupled to the generator shaft. Now in fact the generator starters, in the starter they produce, so this is the in fact the exciter, this is the exciter, and it feeds the power to the field winding of the generator, right. Okay, so this is a DC exciter, structure of DC exciter, and this is the field of the DC exciter, and it is through the excitation control this field current is controlled, and hence the DC power generated from this generator is controlled, and which feeds to the field winding of the main generator, right. So this is the excitation system of the generator. Now let us look at the various faults and abnormal operating conditions in a generator. So if we will consider the electrical faults, so it may happen in the starter as well as the rotor. So therefore in the starter side we have 3-phase starter winding, and in the rotor side we have 3 field winding, right. In the starter 3-phase starter winding, and in the starter what are the possibility of faults? One is your phase fault, that is phase to phase fault involving 2 phases, and then interturn fault on the same phase, and the ground fault. So ground fault happens in fact from single phase to ground fault, or okay, so this is all. And in the field winding the short circuit to the ground may happen because of the insulation breakage, or maybe to the core short circuit. So now if we will see the abnormal operating conditions in the generator, it may be because of the electrical side, and it may be in the mechanical side. So in the electric, if we will consider the electrical aspects, we have 2 components, starter and rotor. So on starter we have 3-phase starter winding, rotor field winding. So on starter will have sometime unbalanced loading. This causes a abnormal condition, not the fault condition. And similarly on the rotor side, sometime we get loss of excitation. Sometime the rotor circuit it becomes open. So that is called the loss of excitation. And the mechanical side, the abnormal operating conditions are loss of prime mover sometime and overspeeding. Okay. So these are the abnormal conditions in a generator. Then if we will talk about the starter phase and ground faults, then obviously the differential protection plays very important role, and it in fact helps us to protect the starter windings, right, starter circuit. So in the starter circuit we have 3 windings for 3 phases, and therefore we can put the 3 CTs in each of the phases at each of the side. So 3 CT at one side and other set of 3 CTs at the other side, right. So we can see here, because under normal condition the current across these 2 sides at the left side and right side will be same. So therefore no need to change the CT ratio. The CT ratio will remain same for both the side. And here we have the restraining and the operating coils, and we can set the bias according to the requirement. So this is a percentage differential relay, very well we have discussed this, and we many times we discussed in case of percentage differential relay. First we talked about in case of differential relay, then in case of transformer we talked, right. So now it is the same thing will be implemented in case of generator also, in order to protect the starter winding of the transformer, right. So this all we know this, and the output terminal is connected through a step-up transformer to the grid. This is how we set the biasing. As the slope changes, the curve may change like this. So this is the trip region, right? Okay, and this is your operating region. So this type of scheme is also known as longitudinal differential scheme. In order to differentiate it from another differential scheme, which is known as transverse differential scheme, we'll see it later in the next slide, which is being used to detect the interturn faults. Okay, so it is this transverse differential scheme is used to detect the interturn. So a name is just assigned, longitudinal differential. This is the normal differential scheme when it is used in case of transformers. But here we call it longitudinal differential scheme because another differential scheme is being in use. So let us see that scheme. So before that, let us see what is the difference of protection schemes in case of power transformer and generator. First is in case of power transformer, the primary and secondary voltages are in general different, but in case of generator, the same voltage for CTs on the two sides of the generator winding, right. So therefore no need to change the CT ratio, and in case of power transformer, turns ratio of the CTs are different because of the ratio of the transformation of the transformer. Turns ratio of the CTs on the two sides of the generator winding is same. And third point is tap changer may be present in case of transformer, which is in fact plays important role, and in case of generator no such device is present. So it is as simple as possible. Therefore the differential scheme known as longitudinal differential scheme caters for phase as well as the ground faults on a starter winding, right. However, it is unable to detect the interturn faults between the turns of the same phase. So it is difficult when there is an interturn fault in the same phase. So interturn faults we can see here now. So interturn faults and how the transverse differential protection scheme plays very important role. So these are the three phase line from the in the generator, right. So this is phase A winding, phase B winding, this is phase C winding. In fact, the detail of the phase A and phase B winding is not shown. So detail connection of the phase C winding is shown. So this phase C winding is split into two parts. If there are two parallel windings, if we can see the connection, and now the CTs are put in two parallel windings in such a way that there must be a spill path and with an overcurrent relay which will detect when there is an interturn fault. Suppose some interturn fault happened here, then what will happen? The current here will reduce somehow. It may become 3000 ampere because here because of the less current flowing through the turns, right. So here we can say because less voltage will be produced when there will be short circuit between two turns, right. So now let us say the current is reduced to 3000 ampere, and let us say under a loading condition 7000 ampere in each phase is flowing, and now here if you will see with the interturn fault in one parallel path it is becoming 3000 ampere, another parallel path it is becoming 3500 ampere. So now what will happen? Because it is transverse connection, it is connected in a transverse fashion, right. We can see here in a cross connection fashion. So therefore the current will flow, the extra current will flow in the spill path. If we can see, if it would have been connected in parallel fashion, then there will be no flow in the spill path, there will be no flow of current in the spill path. So therefore the net current of 5 here it is 5 ampere, it is 4.28 ampere. So therefore in the spill path the net current will flow 0.72 ampere, right. So it is very easy to understand. So in the next class we'll talk more about the generator protection in the lecture 25. So thanks a lot.